This is a twist on a shortening problem. We're going to be using integrals to evaluate or determine the excess area that was produced by a fault propagation fold. We've got a lithotectonic unit here with a detachment or a décollement near the base, and there's been a little bit of displacement, and then this fault propagation fold has been produced. We have this excess area in here. If the layer had not been deformed, it would have continued across, kind of following its base. This lithotectonic unit is 5 kilofeet thick. We're going to determine this excess area, and then from that we're going to infer the change in length associated with this deformation. Now notice that we're going to characterize the shallow fold and the deeper fold by two quadratics. So we have a quadratic for the shallow fold and a quadratic for the deeper fold. We want to figure out this area here. So this is the representation, or the graphical representation of the shallower fold. This is the graphical representation of the deeper fold. We want to determine this area, the area between these two folds. And so we're going to be developing an integral, and we'll be integrating from minus 5 kilofeet over here. Maybe an unusual unit, but English units, and we eliminate a lot of the zeros, so minus 5 kilofeet to plus 5 kilofeet. And so this upper layer has additional shortening with respect to the lower layer, and we want to determine what that additional shortening is. Okay. So if you're going to calculate the area between these two curves, a little problem for you is to think in terms of, we have these two expressions. We want to get this area. Taking a look at it in cross-section form, we want to calculate the excess area in this cross-sectional view. So set up the integral, pause the tape, set up the integral that you would have to evaluate in order to determine this area, or this area here, between these two quadratics. Okay, assuming that you did that, you're going to be, it'll be a definite integral. You'll be integrating over the limits of integration. Actually going to be minus 5 to 5. We're using units of kilofeet. We'll subtract the deeper fold from the shallower fold, and then we'll integrate that function over x from minus 5 to 5. So we have this complex integrand here, minus 4x squared over 25 plus 4 minus x squared plus x squared over 25 plus 1. So, as another exercise, simplify and evaluate the above integral. I think it works well to simplify this integral. You could distribute the definite integration through these four terms and come up with four integrals, but you can combine the terms. We have two terms that are common in x squared, and then we have two constants. Okay, having done that, in simplified form, you hopefully came up with this. So, and this would be the integral that we'd be evaluating and that you would have solved and evaluated. And so let's take a look at the solution. We get minus 3 over 25 times the integral, and we're just distributing the integration here, of x squared dx plus 3, pulling the constant out again, and just integrating from minus 5 to 5 of dx. And so we have, evaluating this integral and evaluating this integral at the limits. The integral of x squared is x cubed over 3, so the 3's cancel out. We still have this minus sign in here. And then the integral of dx is just x, and so we are going to evaluate that from minus 5 to 5. Now a little bit of difficulty comes in with keeping track of the signs here. At least it did for me. I mean, I tend to drop signs if I'm not careful, and maybe you do. I don't know, but we've got 5 plus 5 cubed. That's a negative 125 over 25, which is 5. And then we have minus a minus 5 cubed. So now you should get minus 5, plus 15, plus 15, or 20 kilofeet squared for the area. And I would just dwell on this term here for a minute if you were having trouble with that. Remember, we've got minus 5, which is cubed, which gives us a minus 125. We have minus that, because we have the minus sign here, and then we have minus that since we're integrating at the lower, or we're evaluating at the lower limit. That gives us a minus 125 over 25, which is our 5. So now the shortening is a measure of layer strain, and in this case we're trying to determine the strain associated with the excess area produced by the fault propagation fold. So, but strain in general would be, and this would be shortening as opposed to elongation, would be, we're using an S instead of an E, this would be delta L over the initial length. And so we're determining the additional area produced by the fault propagation fold. Then we divide that by the normal thickness of the layer to get the change in length. So this delta L here. So we've already determined the excess area. If you remember back to the diagram, the thickness of that, kind of the average thickness of that lithotectonic unit was 5 kilofeet. So that's 20 divided by 5. That gives us 4 kilofeet would be the change in length, which I just kind of outlined here. So we have the delta L part. It's 4 kilofeet, but we don't have the initial part. We don't know what the initial length was. We have the change in length inferred from the change in area, but we don't have the initial length. So it's hard to calculate the shortening at this point. We have the change in length. So we need to find this initial length, and we're kind of assuming that it would be the length along the curve y sub s is equal to minus 4x squared over 25. That would be the initial length of that shallow fold if we were to determine what the length of that shallow quadratic was between minus 5 and 5. That should be kilofeet. I want to change that. So that brings us to another integration approach where we have, basically have any curve that we can express analytically. We have a DL, which would be a tiny segment of length along the curve, which can be broken down into its Cartesian components, dx and dy. So the DL, using the Pythagorean theorem, is just the square root of dx squared plus dy squared, which we can rewrite as 1 plus dy squared over dx squared, and we've pulled out a dx here, or a dx squared, which the square root of dx squared would be dx. So when we integrate, we have this in integral form, then we'll be evaluating this integral, and that's what we're going to do next time. So hope to see you then. If you have a chance to kind of think about this and think about, we're going to have to take this is actually the square of the derivative. So you might think of that as dy dx squared, and see if you can evaluate this integral. Okay, next time then, thank you.